Hello, ladies and gentlemen. We are Team 14, Tunnel Wind Power. Our group consists of Brianna Aguilar, Chief Financial Officer, Jose Boteo, Communications Officer, Nicholas Fisher, Chief Engineer, Sam Schroeder, Project Manager, and I, Alexander Rios, Safety Officer. Our client is BART, Bay Area Rapid Transit, who is located in Oakland, California. For more than 45 years, BART has provided fast, reliable transportation to downtown offices, shopping centers, tourist attractions, entertainment venues, and other destinations for Bay Area residents and visitors alike. They have 430,000 passengers per weekday. They save daily riders 1.4 gallons round trip, helping reduce carbon dioxide emissions by 2.7 million pounds per weekday. That's about 27 pounds per rider. BART is always trying to come up with new ways to reduce greenhouse gases and be more eco-friendly. One of the ways that BART is trying to be more eco-friendly is by using a piston effect. This is when passengers experience strong gusts of wind that follow the incoming and outgoing trains. This gust of wind is due to a phenomenon known as the piston effect, which occurs when the air is displaced by a vehicle inside a relatively narrow space.
Our design problem is made up of three components: the design's function, its constraints, and the overall project objectives. We want our design to be able to harness the energy produced by the piston effect and transform it into electrical energy. Our design should be able to generate enough electricity to power BART tunnels wayside equipment. This design's parameters consist of negotiable and non-negotiable constraints. Our team can decide on the location of the device so long as it meets with BART's safety regulations, and we can decide on what voltage output the design has, whether it be 120 over 120 volt, 120 over 240 volt, or 204 over 208 volt alternating current. However, this device must be compatible with the established structures, must be made of non-combustible materials, and every piece and part of our device must come from within the US. The optimal design should have consistent voltage output, be cost-effective, and be relatively easy to maintain. To solve this problem, our team considered an assortment of devices from thermoelectric gradients to piezoelectric devices, but our calculations show that the most efficient design is that of the horizontal axis turbine. Since the majority of train traffic goes one way, we can mount the Savonius turbine to the ceiling of the tunnel to harness wind from primarily one direction. The wind enters the turbine, spinning the blades and generating electricity. This power is then sent and stored in a battery before being applied to the grid and the desired equipment. This power is also monitored, and its data is transmitted through a communication controller to BART's regulatory electrical monitoring systems. The turbine must be compact, as there is little space to construct it between the ceiling of the tunnel and the top of the train, but it must be close enough to the train to capture the most wind while also not being too close as to cause a safety hazard to the train or its inhabitants.
As for the components part of the wind turbine, we have designed an airfoil made out of aluminum alloy. The shaft will also be made out of aluminum alloy with a 1/2 inch diameter and 15 inches in length. Unfortunately, due to the quarantine situation, we had to improvise on homemade experiments, and with the simulations, we managed to calculate an angular velocity of 11 revolutions per second squared. We also calculated the diameter of the airfoil, which is 6 inches. Continuing, the bearing we chose is a shielded stainless steel ball bearing because of its quality. Even though this bearing is shielded, this will have some issues dissipating heat from each ball. However, the bearing will be shielded by contaminants such as dust, and it will have a high strength, and it doesn't wear as fast as a regular ball bearing. We also wouldn't have to worry about the heat dissipation issue because the trains pass every few minutes, and therefore we wouldn't have to worry about excessive wear. The current dimensions of this ball bearing is 1/2 inch housing, 1/4 inch shaft diameter, and a 3/16 inch in width. Since the motor will be harnessing energy in a direct current, we would then need a power inverter that'll convert to AC. This power inverter converts 24 volts directly to 110 or 120 alternating current volts. This occurs because inverters are essentially oscillators that are rapidly switching the polarity of the direct current power source. So this is just simply converting the energy to alternating current, and with the voltage output of 24 volts and 1500 watts. The reason why we chose this DC motor for the generator is because of its efficiency and its price for what it can do. It meets a 5-star RPM rotor for the prototype, and it already has proper voltage coming out for the inverter. The power for this motor is 55 watts, the voltage is 24 volts, and 2.29 amps for a total of 3100 revolutions per minute. There was other motors, but they were just too expensive and it would just be overkill for what we're trying to do. The controller device is essential for harnessing energy. This device will keep us aware of everything that is occurring, the amount of energy being harnessed, components running correctly, etc. This specific model is compatible with Modbus. It has 6 inputs and 11 outputs, and is adjustable via software. The flow of data will be managed by this device and will communicate with other components to ensure that the harnessing system is in working order.
In order to determine the most efficient turbine blade design, we tested 3 blade structures with different cross-sectional dimensions. These dimensions consisted of 1/2 inch, 1 inch, and 2 inch cross sections. We placed these designs in front of a fan and recorded their rotations per minute, or RPMs, at various wind speeds similar to that of what they would be experiencing in the BART tunnels. Across the board, the 1 inch cross-sectional difference proved to have the fastest RPM and therefore has the greatest potential to produce the most electrical power out of the 3 designs. Once we finished testing and finalized the dimensions of the airfoil, we recorded it as a technical drawing. Here, you can see the exact dimensions of the prototype we created, though a scaled-up version would be the one to be installed and utilized in the BART tunnels.
Here's a simulation of a similarly modeled Savonius airfoil in ANSYS. This simulation is showing the air velocities as it hits the airfoil. The red is about 4 meters per second and the blue is 0 meters per second. The red section in the center of the airfoil is important for harnessing as much wind as possible, and demonstrates that this model will spin in the correct direction in real life. Wind speed measurements were taken at the entrance of the BART tunnel with a handheld anemometer. A total of 5 train cycles were recorded to determine a trend in wind speeds over duration of the piston effect. These measurements are likely different than what the final product will be exposed to because the final product will be inside the tunnel where patrons have no access to, including us. The result of one trial is shown in the line graph to the right. The highest wind speed recorded was 8.81 meters per second, and the average wind speed over time was 4.18 meters per second. The airfoil style test compared a Savonius style rotor which features straight fins between the end plates and a helical style rotor with a 180-degree twist between end plates. This test was conducted in a handmade wind tunnel using a wooden box and a 3-speed household fan. Each rotor was attached to a wooden rod which suspended it inside the wooden box. The fan wind speeds closely followed that of the BART underground tunnel, as seen by the anemometer test above. The straight fin and helical fin rotors were evaluated at each fan speed, and the results are shown in the bar graph to the right. They were evaluated by recording the shaft of the rotor with the slow motion camera while having a timer in the frame of the video recording the time in milliseconds. We counted how many revolutions the rotor spun in 1 second and multiplied this by 60 to obtain revolutions per minute. The straight fin motor experienced higher RPM at the same wind speeds, proving its dimensions to be superior to the other, making it the selected style to move forward with. The helical fin proved to be better at initial startup and acceleration, but became ineffective due to the wind primarily coming from one direction, and the straight fin rotor has more surface area to capture a larger volume of the wind. Unfortunately, due to the constraints on the project brought about by the events of COVID-19, we were not able to conduct all our planned testing. Instead, these are the tests that we would have performed under normal circumstances. Vibrations from the wind acting on the rotor will affect the overall performance of the system. Therefore, it is important to test which rotor design has the minimum vibrations at the expected wind speeds. These vibrations may affect the longevity of the installation and the effectiveness of the design. Vibrations of the system are monitored by a 3-axis accelerometer and connected to a controller to analyze the data. After the RPM testing of each rotor design, one optimal design will be selected to determine the power output at the expected wind speeds. We will start at a constant wind speed of 1 meter per second to 7 meters per second, increasing in intervals of 0.5 meters per second, and log the voltage and current produced. The current will be based on a 60-watt load representing a common light bulb. After the constant wind speed tests, we will vary the wind speed according to the anemometer data we received from the actual tunnel wind speed. This will show approximately how much power the design can produce with the periodic nature of the wind tunnel.
Next, we have our economic analysis of our project. From the last presentation to now, we have changed our cash flow to a cost-benefit analysis since it is better suited for our project because the project isn't for profit. So to calculate the benefits, we broke it into 2 groups, energy savings and advertising savings. Energy savings were calculated using estimated power outputs. We based it on the size of the model and on similar models to come up with some numbers since we were unable to test our own device. And advertising savings were based on the assumption that the increased sustainability of the BART would draw in more patrons. So we assumed roughly 750 new patrons annually will be drawn to the BART, and that this will bring an increase in revenue for them. And overall, our net present worth is shown below. Next, we wanted to discuss the environmental and ethical considerations of this project. In regards to the project's environmental impact, it is overall a positive one because the device is intended to generate electricity from a renewable source, being the wind produced by the piston effect. Despite this, it does still have a carbon footprint, and this is from the production and manufacturing of the materials used in our device. In regards to ethics, there are some considerations that should be taken place. BART should always properly maintain the device, and the device should be constructed with quality materials. This will ensure a long lifetime of the device as well as minimizing the risk of failure once it is implemented. Since we were unable to test our device, our final recommendation for this project is further testing. We believe further testing should be conducted before the device is implemented in any way. One of the tests that we recommend is to set up a grid of flow sensors where the device is to be installed so that we can accurately describe the airstream flow of the area. And we also recommend more research in permanent magnet generators for small wind turbines because we're interested in their potential for this project as well. To conclude our presentation, my team and I would like to say thank you all for your attention. Finally, we would like to thank BART for sponsoring this project and for assisting us along the way.